Let me remind you, once it turns yellow, we're counting your warnings, all right? Let's open up here, all right? Let's see what's happening here. Please, the last chapter of the year tells its last verse. We're talking about chapter 6, section 1, momentum and impulse, all right? First of all, apparently we have like 4 objectives we need to achieve them, right? But we probably wouldn't have enough time to get through everything. So what do you think to go by the very first few? Compare the momentum of different moving objects. Compare the momentum of the same object with different velocity. I mean, as you can see, we need to achieve these two. By the end of this period, you will have understood those points. Alright? Let's see how we can do this. Here's a big question for you, but before we jump right in, we need to know what's happening here. This is linear momentum denoted by little p. I mean, don't we just like take the first letter of the word, right? It's momentum, and p, how come, right? Let me tell you, the letter M is already taken by mass. Did you know this, right?
Yes.
But this letter here, p, is coming from the Greek language, which basically is patera. Means the same thing in English. Yes, patera. It's a Greek word. Yes. Petra, right? As you can see, we need to understand this question, and I'd like to hear from you. What's your take on it, basically? What does the cue ball transfer of motion to the black one depend on? First of all, we have to see this video to understand and picture what we're talking about. Let me play this video. Alright, let's see. It's a nice shot, isn't it?
Yeah, so it can go straight, fully straight.
What's your take on it? Like, basically, what are you transferring? I mean, the cue ball, what is it handing over, right? Energy?
Yes.
Momentum, right? I love how smart. Listen, I love how smart you are, because basically we're talking about momentum, right? Yes. I'm not going to be mentioning the word momentum like too often, because we need to figure this out together, right? Let's see how we can do that. So basically we need to know what we are transferring over, what we are handing over. Is it energy, momentum? Is it velocity? It's like trade of velocities, or the mass here makes all the difference. Let's see. We do have 2 other scenarios here. What if the black one were like much more massive, as you can see? Would the cue ball still come to rest? And another scenario here. As you can see, what if the black one were already moving either toward the cue ball or in the same direction? So you have like a myriad of scenarios, right? Don't you?
Yeah.
You have a lot of scenarios.
Yes.
So let's picture this. Let's simulate these scenarios.
Listen, I want to use this.
Yes. What's your question?
Later.
Yeah, tell me.
I want to use the.
You want to use it right now?
Students try the.
Right now.
Yeah.
You can try it home. What do you think? I'm going to upload it on the platform, so check it out. Nice. You know what? I know what you're doing, alright? I know what you're doing.
I'm not breaking.
I know what you're doing. The most basic situation here is just like this. Let's say that this is the black one, this is the cue ball. So 1 and 1 when it comes to mass, alright? This is 1. Velocity here. This one was at rest, right?
Yeah. Careful.
And this one Negative 1. Let's say just like this. I mean, think about what's going to happen. I think you know it. I think you know it, right? Exactly the same as in the video, remember? Do you understand? Yes. Alright. As you can see, what are you basically transferring here? I would like you to think about the product of the mass of the object and its velocity. What is the product of mass and velocity? 1 times negative 1 is negative 1. The product, basically. And right after collision, let's see what happens. What do you say?
The momentum.
Just a second. Before collision, this one was 0, right? It was 0, wasn't it? But right after collision,
The momentum
you know, it's like a switch here. So are you saying that you're transferring the product of mass and velocity, right? That was negative 1 and now it's 0 because you did transfer the product of mass and velocity of the first one, right? All right, nice. If this rule holds true, of course it's gonna like be applied to the next situation, right? Let's just try something else. What do you think if we just change the mass of this one to be 3? You know, it's maximum here. What do you expect? If you say that, just a second, this is too much, alright? You lost your first warning. Too much, calm down, alright? Calm down. Second warning, you move. The third one, a negative phone call home in the middle of class. Where do you go? Not playing around, not bluffing, not making threats. I'll follow through. Remember this. What? What do you expect? What do you expect here? It's going to rebound?
No, I just think that the momentum will divide by 3.
Let's see. I mean, if we are saying that we're basically transferring the product of mass and velocity to the next one, so you must predict that this one is going to appear to be negative 1 because you're basically transferring the mass and velocity of this one, right? Let's see. What? It's not negative 1? So the rule doesn't hold it true? It doesn't. So we have to figure out something else. You know, this is basically what happened before in the past. Through experimental observations, people figured this out. And that's what we're trying to do. What I'm saying is, let's think about each one of them before and after collision. What are you saying? The product again, mass and velocity, before collision and after collision of each one individually. So let me get this back one more time. Remember, we need to use the blue one, right? So MV initial of this one is what? What do you think?
1.
Negative 1. Nice. And MV initial of this one is 0. Great. What about MV final? I mean, after collision, basically.
0.
Negative 1.5.
So MV final here is
0.5.
0.5, which is positive, by the way.
Yes.
All right. And this one, MV final.
Negative 1.5.
Let's get the change of both. All right. Change basically delta here is final minus initial, right? Which is
1.5.
what about the change of this one? Final minus initial.
Negative 1.5.
So are you saying that the change of the product of mass and velocity before and after of each is the same? Exactly. This is the rule, right? What do you think to try out another situation, another scenario, and see if this rule holds true or not? What do you think? Let's say that this is like, it says still 3, just like, this is, let's say, 2.1. Let's make it more complex, all right? And this one, positive 1.3, all right? And this negative 1.6, exactly just like this. And see, let's compare before and after, all right? What do you think? Initial?
3.9
And the initial of this one is?
3.9.
The pink one.
3.6.
And MV initial of this one is
3.1.
3.9. Alright. What about final? Let's make collision here. MV final
3.8.
3.8.
Negative
And
3.2.
MV final of this one.
Negative 3.6.
I would like you to do the math, please, and find the change. Please go ahead. Final minus initial, final minus initial, and tell me if they are the same or not. And you have to expect this, by the way. So change here is equal to negative 7.
Positive.
Point what? 16. Great. And this one change?
Negative 7.16.
Of course.
Negative.
So you see?
Negative
see?
7.16.
It holds true. So here is the thing. Let's come to a conclusion. The change of the product of mass and velocity of each before and after collision is the same. Do you understand? Great. What do we call the product of mass and velocity in physics? This will basically call it momentum, right? So momentum is nothing but the product of mass and velocity of an object. Do you really understand, right? It's measured in what? What do you think? Let's put it in a more scientific word. As you can see, the product of mass and velocity is momentum denoted by little p, right? And as you can see, it's dependent of mass and velocity. If you increase mass with the same velocity, of course momentum increases. And if you increase velocity with the same mass, of course momentum increases. So we can basically say that mass and velocity both are directly proportional to momentum. Do you understand?
Yes.
Are you following, right?
Yes.
Great. It's measured in what? Think about it. Mass is measured in?
Kilogram.
Great. Kilogram, and velocity is measured in? Meters per second. Nice. Of course, momentum is a vector quantity and it does follow the same direction of velocity, right? So if the object is like heading north, the momentum of the object is also northward. Do you understand?
Yes.
Great. Here's a question for you, and based on your understanding, you have to answer this. If you do have a moving ant and an elephant at rest, which one has more momentum than the other one? What do you think?
Moving and
The moving ant. You know why?
because there is velocity and there is
Exactly. Because the elephant is at rest, so velocity is 0, and anything multiplied by 0 is 0, right? But the ant, I don't care how little it is, but it does have mass, and of course, when it's multiplied by anything in the world, when it comes to any little velocity, of course, you end up having a value of momentum, which is basically anyways greater than 0. So we don't care about how massive you are. If you're basically at rest, your momentum is 0, right? Let's think about momentum in terms of a monster. Just like, you know, a monster which wants to chase you or run after you, all right? Think this way. So you cannot run from this monster. I mean, basically, if you think that momentum is a monster and you can outrun it, you cannot do this. Because once you start running, of course, you're going to increase your velocity, and that's why you're going to increase the presence of this monster, right? But if you stop, all of a sudden, what happens to momentum?
Stop.
The monster is
Disappear.
So momentum is like 0, right? So you cannot run from momentum. Do you understand? Momentum is again is what? It's basically the product of mass and velocity, right? Measured in kilogram meters per second. I hope you understand it. I hope you really understand it. What do you think to put it into action right here? I would like you to open your book to page 175. We're going to put this into action. The quiz. Of the quiz. We do have a quiz, but I didn't lose track of time. Do you understand? Page 175. We do have a single law. It's super easy. It's direct substitution of numbers. What are you talking about? P is equal to momentum, mass times velocity measured in what? Meters per second. You understand?
Yeah.
Please go ahead and do it. Please, lights on. Lights on.
Sir.
Yes.
And then you go up like that.
Yes, exactly.
Let's do it.